Hello, welcome back. This is the part two of the relativity lesson for Digital Learning Day 4. Again, it's March 19th, 2020. And we are going to continue with the relativity lesson. Again, I'm doing this in two parts, hopefully, so that uploading the videos and all that doesn't really take too long. And I can get them on there in a decent amount of time today. So now moving over to present mode. Come back to our PowerPoint lesson here. And again, this is where we left off in the previous video with the increase in mass as the velocity of an object increases. And now we are going to look at another really weird effect. And this is called length contraction. So again, with the previous lesson, we were talking about how if you start to approach the speed of light, you're in a spaceship or science fiction kind of spaceship. Nothing we built even approaches this capability right now. But if it starts to move closer and closer and closer to the speed of light, half the speed of light, 0.8 speed of light, 0.9999 speed of light, whatever, your mass increases exponentially and it starts to approach infinity. So it's actually asymptotic, not just exponential. Similarly, not only does your mass increase, but the length of first of all, your own body and whatever vessel you're in, again, this hypothetical spaceship, it will start to contract. It'll literally get shorter along the axis that matches the direction of your motion. So again, here you can see in this image at the bottom, this is what the little fictional spaceship is supposed to look like normally. And from the perspective of the spaceship crew, that's what it will still look like. They will still have a normal perception of their own body dimensions and the dimensions of the spacecraft itself. But from here at Earth, in the top part of the diagram, the perspective here, the inertial frame, if you remember that term from the previous video, it says, or if I'm an observer on Earth, if the velocity of the spaceship keeps again approaching the speed of light, it will seem to get shorter as it moves away. And again, going back to the crew of the spaceship, they will have the opposite phenomenon happen to them. From their perspective, Earth itself and other objects that zip by. So maybe they fly by Alpha Centauri, again, one of our closest stellar neighbors. When they fly by it, they're going to perceive it as being sort of squashed. And this is a weird effect. And if you watch Professor Dave's video on this topic, he'll get much more into the whys and wherefores. There's actually even a way you can calculate how much the length of the object is going to contract. There's a formula to do that with. We don't have to really worry about that. But so as it says here, I'm just going to recap what this point says. It says the length of an object, again, parallel to the direction of motion. That's important. It's not perpendicular to it. It's not getting squashed vertically as it moves away. But instead horizontally. The length of the object moving at tremendous speeds, again, significant fractions of the speed of light, will appear to shorten to an observer who is not moving relative to the object. Again, so your observers here on Earth or so. From the object's perspective, if they flew by a second motionless object, again, motionless relative to them, again, like say Alpha Centauri, they're flying by the star of Alpha Centauri, then the second object, that star, again, will also appear to have its length contract from their perspective. Again, that's all we really need to say about length contraction for now, but again, it's just a weird idea that comes up from special relativity. Now, another weird idea, point 6 for special relativity, is time dilation. And there's actually another way time dilation can occur, and we'll talk about that with general relativity. But here, this is time dilation due to, again, motion with velocity. Again, the past two topics, we've been talking about how significant or tremendous velocities have caused very strange changes. And here the strange change is that time for a increasingly fast moving object, time is actually going to seem to pass slower for them compared to some other observer who is not moving nearly as fast. So again, the greater the velocity of an object, the slower time moves for that object relative to a slower object. And again, so if I'm on the spaceship that's going 90% of the speed of light, again, to me, time doesn't appear to go by slowly. It's not like I'm moving in slow motion as I move about my spaceship or anything. It's just that my clocks, literally, if I have a clock or a watch or the clock on my phone, whatever, the time on that will pass more slowly than it would for, again, my buddy who's back at Mission Control on Earth. Again, I mentioned in the previous video, if you have the means or the ability to watch the movie Interstellar, I really recommend you do this. They have a great scene where there are some practical consequences to this difference in time passing for observers. And for them, it's more about the time dilation is more caused to their proximity to a strong gravitational distortion than it is about velocity. But the effect is the same. The outcome is the same. And of course, the meme that's been generated by this is Matthew McConaughey's character saying this little maneuver is going to cost us 51 years. In other words, well, watch the movie if you want to know more about what exactly he means by that. And again, that's something we might be able to share that particular clip tomorrow or next week. So if we extrapolate this concept of time passing more slowly as speeds approach the speed of light or velocities approach the speed of light, this means then that anything traveling at the speed of light, like say light itself, at least in a vacuum, not slowed down again by air or water or whatnot, actually doesn't experience the passing of time, but instead is always in sort of in an ever-present now sort of situation. And notice here I put weird because again, that's something we can't really wrap our heads around. We can't really imagine there not being a past and a future for our experience. We experience now, and we can understand that, but we always know that it's going to change into a different now, and as we move through time, as time passes for us. But again, that's only for things actually moving at the speed of light. So gravitational waves, which again we'll talk about later in this lesson. Light, of course, other forms of electromagnetic energy, gamma radiation, X-rays, radio waves, anything like that. This effect, this time dilation due to velocity, has been actually experimentally confirmed, which is that's a really cool thing to me about all of this. This is not, we call this a theory of relativity, but it's not really theoretical. We can experimentally demonstrate a lot of this. The stuff about moving near the speed of light, not so much, but some other stuff, yes. So if you can get something to go pretty fast, not even a tenth of the speed of light, but just orbital velocities like satellites have, they will have a significant enough difference in their internal clock speed relative to clocks here on the ground that if you are using GPS, for example, the satellites that provide the tracking service for you, they have to have their clocks corrected relative to whatever receiver is on the ground, your phone, for instance. Otherwise, they're going to get the data, your navigational data, wrong. It's going to be off. And again, that's because those satellites are moving at high velocities, not anything, again, near a significant fraction of the speed of light, but thousands of kilometers per hour, and or really tens of thousands. And at those orbital velocities, they're going to experience some of this time dilation. Now, another thought experiment that has now become real in recent years is something called the twin paradox. And the twin paradox is the idea that, okay, if you take identical twins, which, again, have the same age, if one of them is an astronaut and you let them go on an outer space mission, moving at some incredible velocities, then the twin that will stay home and is not an astronaut, they are going to have time pass for them more quickly than the astronaut twin, who, again, because of their very high velocities that they're moving at in their spaceship, time is passing more slowly for them instead. And so when the astronaut twin returns home from their space mission, they will actually have aged less than their earthbound twin. And so the earthbound twin is actually now older than the astronaut twin. And if, this little diagram down here shows an extreme example of this, the astronaut being still, in their, I don't know, their 20s or 30s or whatever, and then the earthbound twin being now in their elderly years. And again, that is that's good notifications. Anyway, that's an extreme example. A more real example, which is not as dramatic, it has been done with two actual identical twin astronauts, Mark Kelly and Scott Kelly. They're right here. You might be aware of them just because of this whole twin astronaut thing. Both of them have been astronauts. Scott Kelly is the one who is probably more famous, partly because he's running for, I think, Congress right now for this year. But also because in recent years, it was just a couple of years ago, he returned from having one of the record-breaking durations in space. He was on the International Space Station for a very long time. I can't remember off the top of my head the exact uh, duration, but longer than I think anyone previous to him. And his brother Mark Kelly I think he was only operating on space shuttle missions. I don't think he actually ever stayed up on the International Space Station for long duration missions. So while he has gone into space and therefore moved at very high orbital velocities, he spent a lot less time doing that than his brother Scott. And so you have this situation where Mark is now actually older than Scott, because Scott has spent more time, with time going by slowly, more slowly for him than it has for Mark, because he has spent a fairly significant portion of his life moving at orbital velocities, which are fast enough to cause this effect. And of course, these two guys, they've been studied for other reasons as well, the effects of microgravity on the body and things like that. But this is the twin paradox made real, is really where they become significant for our purposes. It's a really interesting scenario, and I recommend that you look into it. Scott Kelly also, by the way, just again, since we're on digital learning days and you've got some time at home, on Netflix, if you've got Netflix, he has a documentary on there. I can't recall the name, but I'll post a link to it later, that gets into some of this stuff. But mostly about his time on the ISS, his very lengthy stay. All right, last thing about special relativity. This is our 7th point, and this is the one you probably know about. This is called mass energy equivalence. Now, you probably don't know that term, but you know the formula. You know E equals mc squared. It's the most famous formula I think there is. Everybody has heard it or seen it, and you can recite it. If I said, what's the formula starting with E equals, you know the rest. And of course, and Professor Dave actually says this in his video about the topic, but of course, most people don't really know what, E equals mc squared means. And it's kind of a simple idea. As far as relativity concepts go, it's not a super complicated or super weird one. Basically, what Einstein tells us with the mass energy equivalence idea is that, kind of like how he already told us that space and time are really one thing, space-time, energy and mass or matter are also one thing. And they're really just two different forms of the same thing, two sides to the same coin, like the saying goes. And we can convert one to the other. And this actually really makes a lot of sense. You know this already innately. For any time you take advantage of a chemical reaction, like lighting a match, eating food to convert the energy or the matter in that food, the mass in that food, into energy that your body can use. Any chemical reaction like that you depend on, you're allowing and taking advantage of the fact that some mass, some matter is being changed into energy. Now, chemical reactions are actually not very good at demonstrating energy mass equivalence because they're not very efficient energy releasing reactions. A lot of the mass that you start with is going to still be mass when the reaction is over. So again, lighting a match. If I light and burn a match, now if maybe I let the match burn for, I don't know, 5 seconds and I blow it out, a lot of that match is still going to be left. And even the part that's not normal unburned wood is going to be, soot, ash, smoke. All of those things still count as mass or matter. And only some of the mass is going to have been converted into energy. Again, light, heat, sound, those different forms or varieties of energy. We have more efficient energy reactions, nuclear reactions. Again, fusion. Of course, we've talked a lot about fusion this spring, and fission as well. Both of those require the nuclei of atoms changing. Fusion is when we combine them. Fission is when we divide them, a large nucleus becoming smaller, or at least two smaller nuclei. And both of those also release energy, and they release energy more efficiently than chemical reactions do. But they still are not 100% efficient, meaning that some of the mass you start with will still be there after the reaction. To have the most perfect or most efficient energy reaction, you want to look at annihilation, which we've actually talked about that recently. Again, about 2 weeks ago, maybe, when we were still talking about high mass stars, we talked about annihilation because, again, a very common, you have a lot of radioactive decay happening in a lot of the nuclear reactions we're talking about with fusion, especially the alpha process. A lot of neutrinos being produced there. And neutrinos are being produced, but in that process, you also get positrons, which are antimatter electrons. And if they collide with a normal matter electron, then both of those, the mass of both of those particles is totally and completely converted into energy, particularly gamma energy. And that is the cleanest, most efficient energy reaction we have. And it's also because of that, it's the best demonstration of E equals mc squared. Now, for the formula itself, we don't really talk about these figures and these variables. E, of course, stands for energy. And here, energy is being measured in joules. It's not being measured in some other unit like mega electron volts or ergs or anything like that. We're talking about joules, which, again, if you remember those from chemistry and physics, should sound pretty familiar. Kilograms is what we're measuring the mass in, so not grams or some other variation of the grams, just kilograms. And then C, of course, is the speed of light. Now, again, here in the text, I note that we're still using that 300 million meters per second value. Here they use the more precise measurement of 299,792,458 meters per second. And again, you can see why we round that up to a clean 300 million, because it's a lot easier to remember. But again, notice that C is squared, meaning we have to multiply the speed of light by itself. And if we do that, we get a tremendous value. If I use the rounded value for C, I get 9 times 10 to the 16th meters squared per second squared, meaning 9 with 16 zeros after them. Now, again, here in this little diagram, they've taken the more precise value for the speed of light, and they've squared it, and they got, well, let's see. That's millions would start there, billions here, trillions, quadrillions. So 89 quintillion, 875 quadrillion, 217 trillion, 873 billion, 681 million, 800 meters squared per second squared. Actually, I think I read that quite wrong. Let me see here. So the millions would be here, billions. Yeah, so I'm sorry, this is in quadrillion. So 89 quadrillion, 875 trillion, 517 billion, 873 million, 681,800 meters squared per second squared. That's the proper interpretation of the value. Sorry about the wrong value or the wrong reading the first time. I've got Athena here. She's my dog helping me out for a minute, I guess. All right, so that's special relativity. We covered 7 points for special relativity between the previous video and this video. Now we're going to look at the other side of relativity, which is general relativity. Fortunately, there's a little bit less to be said here. There's only really 2 main points. Although after we cover those 2 main points, we are going to talk about some ways that we know that all of this is in fact true and not just theory in the way that we typically mean the word theory. These are, again, things that we can experimentally verify and have been able to do so throughout the past century. Some early methods, in fact, one of them dates back to literally 101 years ago, 1919, and then some are more recent, just the past few years. All right, so the 2 main points. The first one is that mass curves or distorts space-time. This is a major concept when you're dealing with very massive objects like planets, normal stars, compact stars like white dwarfs and neutron stars, and of course, black holes. The closer you get to a very massive object, the more that the space-time around it is going to be curved. And again, you can kind of see that in this little diagram here. Now, by the way, I'm just going to go ahead and mention this. Almost always, like you see with these 2 images, and you'll see it on this next slide here, normally when we diagram or try to visualize how space-time is curved by massive objects, we show space-time itself as a 2-dimensional sheet, which is really not the best way to do it, but it is kind of the easiest way to do it. So here, this massive object is maybe, again, a planet or a star. And the closer you get to, like literally, if my laser pointer represents, a space probe or a spaceship or something, as I get closer to that star, let's say it's a star, again, space-time is going to be more curved as I move through it. And again, it's going to be really, really curved as I approach the surface. And this is going to change some things about how just things can happen near this object. This, by the way, this is also true for Earth. We don't really think about it because we live within Earth's gravity well. But if you were to go outside of Earth, like on a really long distance space journey, like say the Apollo astronauts did to the moon, that's kind of as long distance as we have right now for human travel. They actually would have experienced less space-time distortion in the space between the Earth and the moon, because they're getting a little further out from Earth's gravity well. However, they would have gotten closer to the moon's gravity well as they got closer to it. So a little more here. It says that this curving, again, the increased curving as you approach a massive object, It actually also affects the passage of time. And this is what I was talking about earlier in the time dilation part of the lesson, where I talked about how there's another way for time dilation to occur that didn't have to do with velocity, and this is it. So the closer you are to curved space-time, again, it's space-time. Space isn't just affected, time is too. So time is actually going to slow the closer you get to a tremendously massive object. And this little diagram kind of shows how that can happen. For an outside observer, their clock is going to keep ticking as an object moves closer and closer toward a black hole. But at this point, the object is close to a black hole, but not too close. And the clock is ticking at the same rate as it is for the outside observer. So they're both the same distance from the black hole. But now the infalling object, they move closer to the black hole, and the outside observer does not. And now the outside observer's clock is ticking slower relative to the outside observers. And again, this is more of the time dilation that you see presented in the movie Interstellar. Again, it's not so much about increasing velocities causing time dilation. It's more about proximity to a massive object. And again, in their case, that being a black hole. And it's in the movie, it's a supermassive black hole. And we'll talk more tomorrow about what that means. And what's interesting is it's actually the curving of spacetime is actually what, from what we can tell, causes gravity. And again, that's when I say that, that's really sort of an oversimplification of what we understand about how gravity and general relativity work. But again, we normally talk about gravity as a force, and that's a very good description when you're talking about classical or Newtonian physics. But when you bring Einstein and relativity into play, like we've had to do for the past century or more, gravity is really less of a force than it is just a consequence of the curving, the distortion of spacetime. And so it causes things to accelerate by redirecting them through space. It's kind of a weird thing, like most of this stuff is. All right, a little more about the curve of space-time. Since the very shape, if you will, of space-time itself is being changed, then the movement of objects, like this is what I was talking about a minute ago, even light is also changed. Again, this is, when we say it's changed, it's relative to an observer in normal space. So again, if you were somebody who is moving closer and closer to a black hole, you would not really experience this change in time. Nor would you notice that your course is being shifted or redirected or rerouted. You would still feel like you're moving in a straight line. And again, strange stuff, but that's what it would be. Again, from the object moving closer to the black hole, their perspective, things are going to still seem pretty normal until you get right up to the black hole. Then things can change, and we'll talk more about that tomorrow. But for an outside observer, things are going to get really weird. All right, so this means that light can actually be curved by gravity. Now, this is a weird statement because when we say that their paths are curved by gravity, we think, well, oh yeah, well, again, like Newton says, gravity acts on objects with mass. The force of gravity is directly proportional to the product of two objects' mass. So if I throw, a football here on Earth, the path of the football is a curved parabolic trajectory back to the ground, and that's because gravity from the Earth is affecting the mass of the object and it's pulling it back down in a curved path. But when we say that light has its path curved by gravity, we don't really mean that. We don't mean that, okay, well, just like a football I've thrown, gravity is going to pull the light back down toward the black hole. Instead, again, it's more about the path that light can take is being itself curved. Therefore, the light has to follow that path. And so, like it says, this is not because light has mass in the normal sense, but because the route that it has to take has been changed. Kind of like a train having to turn because there's a curve in the track. It's not the best analogy because, again, if you were on the train, you could tell the train was kind of taking a curved path itself. If you were a beam of light and you were moving near a black hole, or even, again, just a star, and having your path redirected by the space-time curve, you wouldn't really notice. Again, from your perspective, you would still be moving in a straight line. And again, getting back toward black holes, they curve space-time infinitely, so that within a certain distance, nothing can escape the gravity well of a black hole. All right, second main point for general relativity, second of two, which is nice. We just have this one main point left, and then we'll talk about some proofs for all of this. And this is called Einstein's equivalence principle. Excuse me. This is not the same as mass energy equivalence we were talking about a few minutes ago. Again, mass energy equivalence is what we mean by the E equals mc squared formula. The equivalence principle has really not much to do with that, at least not on the surface. It's about how you would not really like to yourself as a subjective observer. Um, you would not be able to tell the difference between being in a gravitational field, like say you are right now here on Earth, on the surface of the Earth, and being in an accelerated container, like a box. Um, and the reason for this is they're equivalent experiences. Our bodies have the ability to detect acceleration. We actually can't detect velocity. You may have never really thought about that, but again, like if you're sitting still in a car and it's going at a constant high speed, 80 miles an hour or something, you can't really tell that. You might fall asleep and be none the wiser, taking a nap, going 80 miles an hour down the highway. But you can detect acceleration, and that's why roller coasters are so fun, because they engineer the tracks to have all these ups and downs and turns and curves and corkscrews, and because all of those different changes cause changes in velocity, and a change in velocity is acceleration. And again, we can detect that, so it provides a thrill and a sensation. But gravity, again, acts to accelerate objects. And on Earth, if you're near the surface, gravity will accelerate a falling object at a particular rate, that being 9.8 meters per second squared. Meaning that if I drop a box out of an airplane or something, it's going to fall toward the Earth, and it's every second that it falls, it's going to get faster by another 9.8 meters per second. So 9.8 for every second, meaning 9.8 meters per second squared. If you were to be put into a box, or more, if we elaborate this scenario, a spaceship. If you were put in a spaceship in space, and that spaceship was accelerated upward relative to you, you're standing on the spaceship, you're standing right here, and the floor is perpendicular to your feet, and the spaceship is accelerating you upward. And if its acceleration matched the rate of the Earth's gravity, so 9.8 meters per second squared, you would not be able to tell the difference between realizing that the spaceship was accelerating versus feeling like you were in Earth's gravity. And that's why we call it the equivalence principle. Both of these sensations are equal or equivalent to each other, for the purposes of you as a subjective observer. And what's interesting, and if you've ever watched the show The Expanse, it's one of the shows that, for the most part, kind of takes the whole space travel part of science fiction fairly seriously. And they take advantage of this equivalence principle. What they do is they provide for artificial gravity on a spaceship, not by some sort of just made up gravity engines or inertial dampers or something else that's just come up by a writer or whatnot, but instead they say that their spacecraft accelerate either at or near 9.8 meters per second as they're traveling through space from planet to planet, Mars to Earth, or Earth to the asteroid belt, or what have you. And because they build their ship floors perpendicular to the long axis of the spaceship, they act as an actual floor. So as the spaceship accelerates, the people can walk about on the floor because there's a force pressing against their feet. And again, if they move at or near 1g, which is 9.8 meters per second squared, then it'll feel like they're in Earth's gravity. Now, the part about this that they kind of do have to just kind of hand wave away is that this would be very hard to do in real life, because to constantly accelerate, you need energy. You need, in the case of a spaceship, you need fuel for the engine. And they kind of dance around that. They say that their spacecraft have a special engine that runs off of something called the Epstein drive, and somehow it's a very, very efficient fusion reaction or something like that. But of course, in real life, we only have rockets depend on chemical fuels like oxygen and methane, things like that. And they would run out of fuel very quickly trying to provide artificial gravity by this method. So until we can provide or come up with some sort of engine that could allow for constant acceleration without depleting fuel very rapidly, this sort of method is not going to work. Okay, two famous proofs for general relativity. Again, how do we know this is actually real and not just a theory? One that we actually talked about way back in about maybe November, when we were talking about terrestrial planets, talking about Mercury, is the fact that Mercury does not actually end up appearing in the sky where Newton's laws of physics would predict it would. And these laws of physics actually work for pretty much every other planet. There's some minor discrepancies, but nothing that would, if you ran the calculation and then looked in the night sky where the planet should show up based on that calculation, for most planets, that's going to work out. For Mercury, it really doesn't. There's a significant discrepancy that means that, okay, well, if I say Mercury's going to appear here, when I go and look with my telescope, oh no, it's actually over there. So for a long time, again, Newton, he's developing his theories in the mid to late 1600s. From then until about 100 years ago, astronomers, they just kind of had to fudge their way through predicting where Mercury would appear in the night sky. And we didn't have a good explanation for why this discrepancy existed until Einstein's general theory of relativity was developed. Again, roughly in 1915 is when Einstein would have published this work. And so if you actually calculate using Einstein's equations, not the E equals mc squared formula, but his other equations dealing with general relativity, which we don't really go over or need to, you can end up getting an accurate prediction for Mercury's position. And another effect here, and you can see this, it calls this the precession of Mercury's orbital perihelion. So in more practical or specific terms, what this means is that Mercury's perihelion, which is where it's going to be closest to the sun, don't forget from last fall, Kepler tells us that planets do not have perfectly circular orbits. And actually, Mercury's is one of the more elliptical ones. So it's got, at one point during its year, which again, Mercury's year is only about 88 days, it's going to be a lot closer to the sun than at the opposite point in its year where it's a lot farther. And that's called aphelion, when it's farther. But Mercury's perihelion point actually keeps moving around at a rate that, again, doesn't match what Newton's laws have to say. And again, the other planets do this too, but not nearly as severely as Mercury does. And that's because Mercury is closest to the sun as far as planets go. And the closer you get to a massive object like a star like the sun, the more space-time is going to be curved. And Mercury, when it comes into this perihelion range, it's going to get close enough to really get affected by some of this space-time distortion. All right, gravitational lensing and deflecting is the other one. And we've actually talked about this kind of recently when we talked about a few weeks back how we can detect hard to see stars, things like red dwarfs and brown dwarfs. We talked about gravitational lensing. And we actually, in that lesson, we called it gravitational microlensing because the mass of those objects is not as much as, like a black hole or something. But anyhow, the concept in general can be gravitational lensing or deflecting. And this was first, this is one of the earliest proofs of general relativity. Just a few years after Einstein's publications, the next upcoming total solar eclipse was going to be in 1919. So again, 101 years ago. And a lot of astronomers went to the location where totality was going to be. If I remember offhand correctly, I think it was in somewhere in South America, maybe Peru. I could be wrong for sure. But what they did is, just like how people like to go watch eclipses anyway, solar eclipses, they set up, their telescopes and their other measurement devices, and they were able to actually, because of the dim sky during the eclipse, they were able to see that some stars appeared near the sun, but in a wrong spot based on where they should be. And this was not because the stars were moving rapidly all of a sudden relative to the other stars around them. Instead, the light they were sending past the sun, because they were behind the sun in actuality, was being bent, lensed, or deflected around the sun toward Earth. So we see that light beam coming toward us. We assume it's going in a straight line because that's what it looks like. The position of the star appeared to be here when, in fact, again, the star was actually behind the sun relative to our perspective. And again, this had to be done during a total solar eclipse because normally during the day, the sun is too bright for you to notice any stars nearby it. It's tough to see any stars during the day, even with a powerful telescope. But obviously, a star right nearby the sun is going to be impossible to see during normal daytime conditions. All right, modern proofs. Really just one, and this is called the detection of gravity waves. This is a recent phenomenon or a recent development. Gravity waves are literal waves in the, again, fabric of space-time. So if you can imagine space-time itself, the universe itself, being rippled up and down with a wave moving through it, that's pretty much what we're talking about. And instead of the relatively static curving around objects like the sun or like a really massive black hole or something like that, gravity waves again produce, or incredibly massive objects that are moving, especially in binary systems. They produce ripples in spacetime, like we were talking about. And again, here in this diagram, the example is a binary black hole system. As these two black holes orbit a common center of mass between them, they, just like how if you were splashing in a pool, you would cause ripples. They're kind of doing the same thing, but they are rippling the universe because of how much mass they have individually and the interaction of their combined masses together, along with their motion. And so gravity waves, as we discussed the other day with kilonovae, they take energy out of the objects that release them. So if like again like a black hole binary pair is releasing gravity waves, they are actually, that binary pair is losing energy, like kinetic energy. Their orbit is going to slow, and it's actually going to decrease. Like they will become closer to each other. Their distance will decrease. The orbit will decay, and eventually this is going to cause a collision. They'll meet. Their orbits will decay so much that the two will have to collide. And this, some other common sources for this. Again, we talked the other day about how kilonovae were caused by neutron star binary pairs or a neutron and black hole binary pair. We don't normally talk about kilonovae being produced by two black holes in a binary system, but all three of these options, all three of these combinations can produce these gravitational waves. And again, these can be detected at tremendous distances because of the amounts of energy being released, especially when the actual collision occurs. And if you've been watching or getting around to watching the Black Hole Apocalypse video, we'll get into some of that. And some of the other videos I posted on my YouTube channel playlist today for Relativity, they also talk about this as well. Especially the one from the physics girl where she goes and visits the LIGO observatory. Definitely check that one out. And in fact, that's this next topic here. It says gravity waves are detected by what we call gravity interferometers, such as LIGO, which is a facility called the Laser Interferometric, that's a fun word, Gravity Wave Observatory, which was actually built and put into operation back in 2003, but it wasn't able to detect any confirmed gravitational waves until 5 years ago, 2015. And they do this by sending lasers down two perpendicular, very long, actually each one is 4 kilometers long, tubes. And if one of the lasers has a delay when it returns, because there's mirrors at the end of both of these tubes, and they both hit a detector, if one of them has a delay, that's because a gravity wave has passed through the Earth, including these 2 detector tubes, and it has actually meant that it has stretched the space of one of the tubes, meaning that one of the lasers actually traveled a farther distance than the other laser. It's a crazy concept, but that's how it works. And this is a nice little diagram that I found last year that kind of helps demonstrate this. Again, the laser itself is produced down here at one end of the facility. And when it's fired, it goes through this beam splitter, and that's what separates it down these 2 4-kilometer distance tubes. And again, there are mirrors at the end of both, and the light waves bounce and return. And when they come to the light detector, which is over here perpendicular to the laser, again, if they are moving in phase, they're going to cancel each other out, and the light detector just won't see anything. There will be no light detection. But if the 2 lasers are moving out of phase because they're no longer moving, they've no longer traveled the same distance, and now their crests and their troughs are they're no longer aligned. One of the 2 lasers is going to get through this beam splitter, and it's going to hit the light detector, and it's they'll know that, oh my gosh, yeah, a gravitational wave has passed through. And that is everything from the lesson. Again, there's tons of supplemental information about these concepts. Again, I haven't posted the supplemental videos to eClass yet today, but if you go to my new YouTube page, which you can find by going to the embedded video from yesterday on neutron stars, you'll find this playlist I have on relativity. There's another playlist on stellar life cycles and end stages, but the relativity one has, and let me go back to where I'm sharing my screen so you can see exactly what I'm talking about. But again, if you go back here, there's again a few different videos I've got, and they're all great. Again, some of them are very specific, like the Professor Dave videos about particular topics. Some are just more about the LIGO detectors in general, or about gravitational waves. Again, the Mercury, the orbit of Mercury and how it's different. And so I definitely take a look at least 1 or 2 of these that can help expand what we've been covering. All right, so I'm going to stop presenting, and that will be the end of our relativity lesson. See you tomorrow.